But now the recording is launched.
Okay, you have to give me the right to share my screen.
Yep, it should be fine. Can you try it?
Yeah.
Okay.
So great. You see my screen now?
Not at the moment.
Now you should see.
Okay, now it's better. Okay.
Okay. So, oops. So yeah, I didn't have time to write with LaTeX everything, so I did it by hand. I hope you can read. So the purpose is to give, there will be 3 parts. One, which is a classical theory. The other one below, which is some problems. And the other one, which is the identification problem, okay? So let's begin with classical theory. I guess most of you know it or are supposed to know it. So let's begin with households. There is a finite number of households indexed by I. Each household is equipped with a consumption set. For simplicity, let's assume it's just the non-negative part of R at the power of L. L is the number of commodities. Omega I, which is strictly positive, is the initial endowment. And UI, which maps the consumption set into R, is a continuous increasing quasi-concave utility function. And P in RL plus is the price vector, okay? You interrupt me if there is anything you don't understand. So each household is supposed to maximize his or her utility function given her or his budget constraint, namely the fact that the value of xi at the price P should not exceed the value of his or her initial endowment, and the consumption good xi should belong to his consumption set. So here you have the graphic illustration of this. You have 2 goods. The diagonal straight line is the boundary of the budget set. You see the price vector, and you have an indifference curve, which is a set of combinations of x1 and x2 for which the utility of the consumer is constant, which is exactly tangent to the budget set at the point xi star, which means that xi star solves the demand, the maximization problem here, in the sense that the gradient of the utility of the agent at xi star is exactly collinear to the price vector, which means that the first order condition of the maximization program is fulfilled. And therefore, xi star is part of the demand of household I at the price P. Now, this is for households. Now, for production, you have capital N firms, J from 1 to N. Each firm is characterized by a production set, which is a subset of R at the power of L. And so you have an illustration on the left here. So negative quantities are inputs, positive quantities are outputs. So in this example, X1 is an input, X2 is an output, and the shaded region is the production set. That is, it's the combination of input and output which are technologically feasible. Obviously, the most interesting part of the production set, is the boundary. And here in this example, since the production set Yj is convex, this means that we have decreasing returns to scale in a broad sense, okay? Now, what the producer tries to do is to solve this problem, to maximize its profit given the technological constraints imposed by the shape or the geometry of Yj, the production set. And so graphically, here you have an illustration of that. This means that if you have a price vector P, which is given, exogenously given by the market, then you look at the gradient of the production function, whose graph is exactly equal to the boundary of the production set, if this production function exists. And then you have to find a production vector, Y star, which is such that the gradient of the production function is collinear to P. And then you have I put it here, I don't know, you see it here. That's the profit, which is earned by the firm. So here you have the same story, but with constant returns to scale, which means that the production set is a cone, which means also that profit is equal to 0 necessarily. And here you have a situation with possibly increasing returns to scale, and especially with fixed cost, which means that here you have to destroy or to consume a non-negative, a positive quantity of input without producing anything. that's a fixed cost. And after that, the production set here is not convex, which means that you may have increasing returns to scale, okay? And in this case, very often it's easy to find situations where the profit is negative. Of course, the production set concept is much broader than that of production function. In particular, with the production set, you may have joint production, which is hard to formalize with a production function. So yeah, and of course, when Yj, the production set, is non-convex, then the maximization program of the producer may fail to have a solution. So this has been an ongoing problem in the 50s and the 60s, first tackled by John Kenneth Arrow, General Debreu here, who are, so to say, some of the founders of General Equilirbium Theory. And one of my colleagues and friends who worked a lot on non-convex production is Bernard Cornet, whose picture you see here, who is now retired. So variation equilibrium, what is it? It's a bundle of consumption baskets for households, production plans for firms, and a price vector P star, such that what? Such that for each household, Xi star is a solution of these households' utility maximization program, and Yj star is a solution of firm J's profit maximization program. P star must be a price vector, so non-negative, and you must have equality of supply and demand. So supply is on the right side. That's the sum of the production plans of all the producers. And demand is on the left side. That's the net excess demand from households. So XY star is the demand minus the initial endowment, and that's the excess demand, the net demand, and you sum over all the households. So that's the concept of a variation equilibrium. Now, it's well known, at least since actually it was known more or less already earlier in the late 40s, but anyway, that if everything is continuous and convex, then all these problems are completely classical, and then you can have an equilibrium, which is a fixed point, actually. You cannot just rely on the Brewer, the classical Brewer fixed point theorem. You need to rely on the Kakutani fixed point theorem. So what is a fixed point theorem? It's a theorem that tells you, for instance, in this very simple example here, you have a function f, which is continuous from the 0,1 interval to 0,1. 0,1 happens to be compact and convex. And so if you look at the graph of f, there must be an intersection between the graph of f and the first diagonal y equals x, okay? So in this intersection is a fixed point. Now, Kakutani, and Brewer fixed point theorem essentially tells you that's all you need. Every function which is continuous on a compact convex domain admits a fixed point. So a Kakutani fixed point theorem is slightly more elaborated. It deals with correspondences, that is set valued maps. So capital F maps the 0,1 interval into the set of subsets of the 0,1 interval. So here you have a typical graph. And then what you need to do to recover a fixed point theorem is you have to extend the continuity concept for functions to correspondences. So here on the left, the correspondence is not upper hemicontinuous, it's only lower hemicontinuous, which is not good for a fixed point, but on the right, it's okay. So I don't plunge into all the details. This is well known from those people who work on these issues. Let me just illustrate the fixed point, the strength of fixed point theory by this. If you are drinking your cup of coffee, as I'm doing now, right now, and you impulse this kind of rotation inside your coffee cup, there must be a fixed point. That is, there must be a point which doesn't move. Whatever the way, even very, very chaotic, you are putting your spoon in the coffee. Just why? Because the surface of your coffee, which is a disk, is convex and compact, and hopefully you don't create discontinuities in the liquid. Same story here. If you take, but that's slightly more elaborated. If you take, let's say, a map of this place here, Scotland and the north of UK, and then you just move the map and you put it at random over the first map, then there must be a point which is fixed, which is exactly located at the same place on both maps. even though, as you obviously see, Scotland is not convex. But then what is really at stake here is the fact that it's contractible. That is, that there is no hole in it. So actually the real concept which is behind fixed point theory is not convexity. Convexity is a very simple geometric concept. The real concept is that it's contractible. In other words, that the first homotopy group pi1, is non-zero, or is equal to actually 1 point. And so as soon as you have this kind of set, which is obviously compact, non-convex, but contractible, then you have a fixed point. So here, by contrast with a donut, there is a hole, and you can imagine a rotation on the donut, and there will be no fixed point. So the main difference here between the donut and, let's say, your coffee cup is that there is no hole in the coffee cup, and there is a hole here. And this really matters because then you may fail to have a fixed point. Therefore, there may not exist any equilibrium in your economy. So one of my first papers, 2001, if I'm correct, gave a proof, a very general proof of existence with non-convex production using this kind of tools from algebraic topology. Now, if we go a little bit further above just the mere existence, so we have to define the feasible set. The feasible set is the set of consumption baskets, production plans, such that you have equality of supply and demand. Okay, that's the feasible set. So every equilibrium, of course, belongs to the feasible set, but of course, the contrary is not true. A feasible allocation of consumption and production need not be an equilibrium. Now, Pareto optimum is a feasible allocation of consumption and production, such that there is no alternative allocation, which is feasible and which is such that nobody is worse off, so that every household has at least the same level of utility with the new consumption bundle as with the old one. And there is at least one guy who is strictly better off with the new consumption bundle. So if there is no such alternative, it means that the initial allocation here was Pareto optimal. Okay. And so the first welfare theorem, as you probably know, is that under assumptions which are considered as being standard, which are convex and continuity assumptions, then every variation equilibrium is Pareto optimal, and you have vice versa, the second welfare theorem, which tells you that every Pareto optimum can be turned into a no-trade variation equilibrium by choosing the right price vector. How do you illustrate this graphically? So you have the Edgeworth box here that everybody knows, I guess. So you have two agents, two goods. On the left bottom, you have the consumption set. The origin, O1 is the origin of the consumption set of household one, and household one sees everything from this point, and household two sees everything with the inverse perspective. So O2 is the origin of the consumption set of household two. And then here you have an example of a Pareto point at the intersection of the two indifference curves, where the two gradients of the two utilities are collinear, which is the hallmark of Pareto optimality. And here I have drawn also the Pareto curve that you see here, which starts at each corner, because if you give everything to one agent, and if preferences are strictly increasing, then this is already Pareto optimal, even though it's completely stupid. And then you see, it's easy to prove that with some smoothness assumptions, then the set of Pareto optima is a submanifold of the Edgeworth box, which in this case, in the 2x2 case, is of dimension 1, exactly 1. So you have an indeterminacy of Pareto optima, and the question is, which Pareto optima are selected by the variation equilibrium concept? And the answer is here. So same story, it's an Edgeworth box. You have the initial endowment omega here, and then, and then you have the two indifference curves which cross the initial endowment. So if you look at this, probably you cannot see it, but yeah, this region, this area here, yeah, that's the area which is mutually interesting for both agents, where they are going to try to find an agreement according to thanks to the market. And so here you have an example of a variation equilibrium, which is Pareto optimal, which means that you have a price P, you have the budget boundary for each agent, and it coincides, of course. That's the whole trick of the Edgeworth box. And they both agree that they should trade from omega to the new point. Okay, so I guess all this is well known. So you have another, here another illustration, which is better done than my own small drawings, but it's essentially the same story. Okay. Now, we have existence, we have Pareto optimality. Now, generic local uniqueness. This is a work that has been done essentially by General Debreu and Steve Smale. So here you have a picture of Steve Smale, who got the Fields Medal in mathematics. So you parameterize the economy by initial endowments, as you see here. So initial endowments are part of the interior of the positive part of the vector space of consumption. And what it's not very difficult to prove is that for a generic subset of initial endowments, there is a finite number of variation equilibria, and each variation equilibrium depends locally and smoothly upon omega. So the typical illustration is here, and what is behind this is the well-known theorem in differential topology, which is called Sard's theorem, the theorem by Sard. So which is the following. So the x-axis here is the space of initial endowment, capital omega. The y-axis is the space of prices. And so the manifold in red that you see here, it's the equilibrium manifold, which means that if you take a typical point on initial endowment, which is between the two critical economies that I have highlighted, then typically you will have three equilibrium prices, and they will move smoothly if you move a little bit the initial endowment. Now, of course, if you go to the right and you hit the critical economy, which is on the right, then as you see, the two top equilibrium prices will shrink into one single equilibrium price, so that at the end, on the critical economy on the right, you have only two equilibrium prices. So there you have what we call in mathematics a catastrophe, in the sense of René Thom, catastrophe theory, which means that you had three equilibria and now you only have two of them. Same story if you go to the left. So essentially what Sard's theorem tells you is that under good smoothness conditions, then you have the set of critical economies is of empty interior and of zero measure, which means that the set of regular economies, the complement of this, is generic in the sense that it's dense, open, and a full measure. Okay, so the conclusion is very optimistic. So we have a kind of theory, and this was the state where we were in the early 70s. We have a theory which tells you that we know that under apparently very general conditions, there exists an equilibrium. It is Pareto optimal, and it is very regular, and there are only finitely many such equilibria. So, if the economy is not too far away from one single equilibrium, it's as if you would have global uniqueness. We don't have global uniqueness, and this was a big question for a lot of people. And it's impossible to get global uniqueness. There are many counter examples and theorems, but at least we have local uniqueness. Which is fair enough for policy. At least that's what people thought in the 70s. Now, let's go to the second generation, let's say, of people working in general equilibrium theory. And they're starting in the 70s, this is where people started realizing that there are some problems. First, there are problems if you introduce incomplete markets. So incomplete markets is a very simple idea. It's the fact that you assume that there are two dates, t equals 0 and t equals 1. So t equals 0 is today, t equals 1 is tomorrow, and tomorrow you don't know whether it's going to be sunny or to rain. And so there is a finite number of states of nature, S1, S2, etc., S capital S. In each state of nature, you will have a given initial endowment. For instance, suppose that the season was very nice for your crops, so you have a lot of production, in state S1, and in state S2 you had a drought, so you don't have any production or very little, you see. So in any case, at time t equals 0, you don't know which state of nature is going to be selected. It's going to be selected at random. You know the probability distribution. Whether you know it, the theory does not tell it to you, but anyway, you're supposed to know it. And what you're going to do is to try to maximize your expected utility with respect to what you consume at time t equals 0 and what you will presumably consume at time t equal 1. Now, of course, we are in a sophisticated world, so we are no longer in the Middle Age. So in order to have some insurance against the risk that you are facing tomorrow, you can buy a financial asset, J, whose return is captured by a vector AS of J in each state S. So AS of J is the vector of commodities that asset J is promising in case you would buy it today at times t equals 0, and in case at time t equal 1, then state S would be selected by nature. Okay, so now your consumption set is R at the power of L times S plus 1, because you have S state in the second period and you have 1 state in the first period. And you also face a new price vector, which is the price of assets, and there are capital J assets. Okay, makes sense for everybody? Now, if you think of this economy in terms of the old-fashioned, Giraud-Debreu budget set, then you would say, well, the budget set is exactly the same as earlier, except that you have a larger consumption set. So the budget set is the set of consumption allocations for agent I belonging to R at the power of L times S plus 1, such that the budget constraint is fulfilled here. Okay, but now we are not facing this Giraud-Debreu budget set. The budget set that people are facing is slightly more complicated because people have to buy financial assets in order to ensure, to hedge themselves against the uncertainty in the second period. So now a budget set is a bundle of consumption, xi, and also a bundle of portfolios, theta I, for each agent I, such that in the first period, your budget constraint is fulfilled, meaning that given what you have to pay in order to consume xy0, taking into account your initial endowment in state 0, you also have some free money, possibly in order to buy some assets. But in any case, you cannot, there is no money for free. So, so if you buy too much securities or financial assets because you are really risk adverse, you will consume less today. So you have a trade-off between consuming more today and hedging yourself against tomorrow, against uncertainty tomorrow. Now, tomorrow in each state S, you are going to consume XYS, but now you have your insurance company, which works, which means that in state S, each asset J will provide you A of S. There is a J which is missing here. I can add it. Sorry, I forgot it. Oops, here. So each asset J promises A J of S, and you have theta I J of them. The price of the commodities is PS. So you have this wealth tomorrow here, and this is what you consume. Okay. Now, so obviously this budget constraint, budget set is more complicated than the traditional Giraud-Debreu budget set, but you would see under certain conditions they coincide. So in any case, the financial market is characterized by this matrix, which is the matrix of returns, which can also be written this way when you try to disaggregate among assets. Now, this matrix A turns out to be key because if it happens that when you look at the span of the vector space, which is spanned by capital A here, given any type of prices, if you find exactly LS here, then this means that markets are complete. In other words, you don't lose anything in jumping from the Giraud-Debreu budget set to the financial budget set here, because essentially you can duplicate any kind of transfer of wealth between states, thanks to the right portfolio. Okay, so if here your matrix A is such that with this matrix A, you can span pretty much everything in the second period, then you're fine. You just need to find the right portfolio allocation, and you will be able to mimic any transfer of wealth here, thanks to the correct portfolio here. Okay. In this case, as I said, markets are complete, and you have a kind of homology between the two budget sets. Okay. Now, what is an equilibrium? A financial equilibrium here is a price for commodities, a price for assets, consumption allocation, and portfolio allocation for everybody, such that the allocation of consumption and portfolios solves the maximization program of each agent. And so you are here, you could write it as being, for instance, U0 plus the expectation according to some probability of your utility in the second period. Okay. Provided, of course, the consumption bundle and the portfolio belong to the budget set, and you have here equality of supply and demand in consumption, equality of supply and demand in assets. So this is typical of the pure exchange economy with incomplete markets. If we had production, then of course here we would no longer have zero, and here we would no longer have zero, which means here we would have, as you remember, productions by firms, and here we would have stocks issued by firms. So that's the simplest situation here, which is the situation where we have no production. Okay. So when markets are complete, it's not difficult to prove that you have a homology between variation equilibria in the Giraud-Debreu sense and financial equilibria. But the main difference is that now it's clear that in order to solve this maximization problem, which is, you maximize your utility in this budget constraint, in this budget set here, you need perfect foresight, because you need at time zero to know not only the price that is prevailing, today here, this one, but you also need to know the price in every stage tomorrow for commodities. And this, of course, it is not given. So you have to anticipate it, and you need to have perfect foresight for that, okay? So to a certain extent, it looks like much stronger from an epistemic viewpoint. And of course, as you can imagine, this has been a hot topic. An example of an economy with incomplete markets, intrinsically incomplete markets, is an economy with overlapping generations. So OLG, overlapping generations, it's an economy which is usually with an infinite time horizon, where you have generations which emerge every, let's say, every time, every period. But then the problem, markets are incomplete because if you get born, let's say, in 2000, you cannot trade about what happens earlier. And you cannot trade about what will happen after your death. So essentially, you have an incomplete access to markets, which means you have incomplete markets, which means OLG is a specific case of an economy with incomplete markets. Now, it happens that as soon as markets are incomplete, and as soon as you have at least two commodities, and that's key, then you have a number of negative theorems. So then I will pause 1 minute just to drink some coffee and also to ask you the very decisive question: do you believe that in real life markets are complete? So I guess the answer is no. Now what's happening when markets are incomplete? So first, generically, that is for an open and dense subset of parameters of the economy, equilibria are not Pareto optimal. So the first welfare theorem fails. If you pick an economy at random, you have zero chance of having chosen an economy such that equilibria, financial equilibria, will be Pareto optimal as soon as markets are incomplete, and whatever being the size of the incompleteness of markets, and as soon as you have at least two commodities. It's even worse than this. Generically, equilibria are not even second best optimal, which means that which means the following. You could say, well, Pareto optimality is too demanding because for Pareto optimality, you look at every feasible reallocation. Remember the feasible set here. And so you take any element of the feasible set that you compare with your allocation. Now, if markets are incomplete, obviously, if you go back here, the budget set is strictly included here in the Giraud-Debreu budget set, and the feasible set is strictly smaller than the feasible set in the Giraud-Debreu sets, because there are transfers of wealth that you cannot do just with the right portfolio. So you are constrained. So you can define the second best Pareto optimum as being a Pareto optimum, where you define the feasible set not as being, the complete feasible set in the Giraud-Debreu sense, but the subset of the feasible sets which is attainable given the financial assets which are available in the economy in the first period. Then you have a weaker concept of Pareto optimality, which is called second best Pareto optimality. But then the very disappointing negative result, which has been proven by John Giannakopoulos and Herakles Polemarkakis in 1986, is that even with this weaker second best Pareto optimality concept, then generically equilibria are not second best optimum. So they are deeply inefficient. That's the conclusion. Now, when you say this, of course, then, this has been discovered in the 80s. It was a big, so to say, theoretical scandal for a number of people. And then in the early 90s, some people said, well, it's not a big deal because we are so clever in Wall Street that we are creating every day new financial assets. So we are decreasing markets incompleteness. And it's true that if you go back to the budget set here, so if you increase the number of assets, of course, you don't create new assets which are just linear combinations of old assets, which is completely useless. So you create new assets which are orthogonal to the vector space, originally spanned by, your return matrix. Then you increase the dimension of the spanned vector space, and then you reduce incompleteness, you see? And so there was this hope that by increasing the span of the return matrix, you would decrease markets incompleteness, and then you would decrease inefficiency of equilibria. And then it has been proven by Ronel Ellul, 1995, that unless you add the ultimate financial asset, which turns markets into being complete, so if markets are still incomplete after your own financial innovation, then actually financial innovation may even worsen in the Pareto sense, equilibria. In other words, suppose you start with, let's say, 10 financial assets, and the dimension you should span is like 20. So markets are incomplete. You have a gap of a dimension which is 10, 20 minus 10. Then you create a new financial asset, which is orthogonal to the previous ones. So the dimension of the spanned vector space is now 11. So obviously you reduced markets incompleteness. And then what has been proven by Ellul is that still there, it might be the case in a number of circumstances which are not pathological, that equilibria with the new economy with 11 assets are even worse in the Pareto sense than equilibria in the economy with 10 assets. So the question is not the size of the incompleteness of markets, it's a 0-1 question. Either markets are complete and then you are fine, you're in heaven, so to say, either or markets are incomplete, and then whatever being the size of the incompleteness, that's the curse of incompleteness, markets will be deeply inefficient, okay? Moreover, as soon as markets are incomplete, generically, equilibria would not be locally unique. So, which means that the nice theorem that you had proven by Debreu in the 70s here, which is that usually, generically, you have a finite number of equilibria, which behave smoothly as a function of the parameter of the economy, which here is the initial endowment. This is no longer true. Within complete markets, you have typically a full manifold of equilibria associated with one parameter of the economy, which means that you have very deep indeterminacy of equilibria. So those guys who proved all these negative results in the 80s are John Giannakopoulos here, who is at Yale, and Heraklis Polymarkakis, a good friend, who is at, I don't know actually where he is today. I think he's in the UK, but I don't remember exactly where because he moved a lot. So that's not the end of the story. Moreover, existence may fail. So there was a very famous counterexample by Oliver Hart in 1975, showing that with incomplete markets, you may fail to have existence of an equilibrium. And so it has been proven later on by Darrell Duffy, John Giannakopoulos, and some others that you can restore existence only generically. So remember that earlier with complete markets, we had existence no matter what, given provided you have some continuity and convexity assumptions. Now, even with continuity and convexity assumptions, you may not have existence, but only generic existence. Fair enough, people would say, well, if you pick an economy at random, you have a 100% chance to find an economy for which there exists an equilibrium. Okay, but then there is a young guy who was a friend of mine, Takeshi Momi, Japanese, who proved that if you add production to an incomplete market economy, then existence may fail in a robust way. That is, not generically. You may not have generic existence. You may have an open neighborhood with a non-empty interior of parameters of the economy for which there is no equilibrium. So the probability of picking, an economy for which there is no equilibrium is non-zero, and it might be quite large actually. We don't know. So even existence is threatened if you have incomplete markets. What I have proven in my paper with Antonin is that it's very bad in the sense that equilibria are compatible with a liquidity trap and Fisher deflation, but I don't have time here to enter into these details. Another beautiful result, which is an old result by Yves Balasco, 1989, is that when you have incomplete markets, equilibria are subject to sunspots. So what is a sunspot? Here you have a picture of a sunspot, which is actually a phenomenon which is linked to the magnetic field on the surface, of the sun. And so we see some black spots at the surface of the sun, which is due to this magnetic phenomena. Now, this is a metaphor to describe completely irrational behavior on financial markets, which is what is illustrated here. So the usual story is the following. Suppose that tonight at the TV news, the star on CNN says, well, ladies and gentlemen, the situation is very, very bad because some astrophysicians in California have seen sunspot on the sun. And therefore, tomorrow, the euro will fall down. There will be a free fall of the euro on foreign exchange markets. So if you watch TV at this time and you are smart because you follow our seminar, you know that there is no causality relationship between a sunspot on the sun and the level of the euro on the foreign exchange markets. So you just laugh or you smile and you say, well, CNN is not improving in the quality of its news. But then suppose you are a trader in Wall Street and you have a lot of euros in your portfolio. You have like millions of euros. You think, well, I'm smart because I went to Georgetown, I'm a Hoya, so I know this is bullshit. But there are so many stupid people on the financial markets that they will believe what CNN told them. So they will probably sell euros tomorrow morning, at 8 o'clock when markets open, or 9 o'clock. And so if I don't do the same, I will lose money. So even though I know there is no relationship between sunspots and the price of the euro on foreign exchange markets, the best thing I can do is to behave exactly as if I would believe that this is true. Because otherwise I will lose money. I cannot bet against the market. So I will sell euros tomorrow morning, and then I will contribute to the panic on the euro market, and the euro will fall down. And so tomorrow night, the same star on CNN will say, ladies and gentlemen, I have told you that we would have a big financial crash on foreign exchange markets for the euro, and this happened. So this is a self-fulfilling prophecy. So what Balasco's result shows is that as soon as you have incomplete markets, equilibria are subject to these kind of stupid self-fulfilling prophecies. There is no way to immune yourself against that. in order to immune yourself against that, you would need to have a financial asset that provides you with an insurance company against everything that is said by people on CNN. And obviously you don't have this. So a very concrete example of that, which I probably already told you, some of you, is what happened in, I think it's 2002. At the time I was working on financial markets, and it happens that Bush went to Japan. And as you know, Japan was already back then engulfed in a big deflation since the early 90s because of the financial crash that Japan experienced in 1990. So Japan was experiencing a deep deflation. And Bush, after having met with the prime minister, maybe Shinzo Abe, I don't remember, gave a press conference and said, well, you know, ladies and gentlemen, the situation is very harsh in Japan because Japan is experiencing a deep devaluation. So probably he didn't know the distinction between devaluation and deflation and could not really read his notes, you know. And so everybody was watching CNN on every financial market on the planet, and everybody thought, well, the president of the United States is announcing a big devaluation of the yen, the Japanese yen. So we should sell the yen. So everybody immediately sold the yens, and the yen indeed lost something like -1, -2, -3% within a few hours, which was a catastrophe, of course. Then the prime minister of Japan had to organize a counter press conference explaining, no, there is no point in organizing a devaluation of the yen. It's just that President Bush does not know what he's talking about. He wanted to speak about deflation, not about devaluation. So then everybody could breathe and say, well, deflation, we know that Japan is in deflation, okay, it's not a big deal. And then everybody would buy again yens. And so that the yen would recover the loss of, let's say, -3% it had experienced within a few hours. So this is a typical sunspot. And I can tell you this happens every second day on financial markets. So the beauty of the theory is that it tells you as soon as markets are incomplete, this can happen every day. Of course, when markets are complete, then this cannot happen, okay? Now, the second problem, so it's a B here. I made a mistake. Here it's a B. The second problem I wanted to mention is linked to perfect competition. As you know, perfect competition is definitely the bread and butter of general equilibrium theory. And it is also, of course, assumed in the very definition of an equilibrium, even the budget set, even within complete markets. Because even within complete markets, if you go back to the definition of the budget set here, you see that agent I takes prices as given. Not only prices today, P0 and Q, the price of assets, but also prices tomorrow. And agent I even anticipates perfectly prices tomorrow. So definitely this is a perfectly competitive setup where you will assume to begin with that everybody is price taker. So this is, as you know, a general characteristic of general equilibrium theory, whether markets are complete or not. And this is linked deeply to the assumption that first, everybody is price taker. So firms are also price takers. And the aggregate demand is a decreasing function of prices. So sorry, it's the opposite here. It's exactly the opposite. The aggregate demand is an increasing function of prices. So now if you write PY, the inverse demand, so usually people assume that, no, it's okay. So aggregate demand is a decreasing function of prices. So now if you write the inverse demand, which is the price P, which works if you observe the demand Y, so you take the inverse function of this aggregate demand here, okay? Then usually we assume that the inverse demand function is decreasing, which you see here, okay? And on top of that, we also assume that everybody is price taker. In other words, that prices do not depend upon the production program of firm J. So you have these two assumptions, and they are key for the existence of an equilibrium. And they are key, not for the existence, but for the usual comparative statics that we do in microeconomics. And they are also key, and this is also key for the very definition of perfect competition. Okay. Now, the main remark made by Steve Keen and Russell Standish in 2007 is that both assumptions are not compatible. So the main argument is here. It's very simple. So if you look at the derivative of the investment function as a function of the production plan of firm J, so as I said, this should be equal to 0 because of the price taking assumption. But this obviously is also equal to the right-hand side here, where you divide and you multiply by dy. And so since dy divided by dyj is equal to 1, why? Simply because y is equal to the sum of the yj here, okay? So then, of course, this is equal to 1, and then the right-hand side is dp divided by dy, which by assumption should be strictly negative. So you have a contradiction here. You cannot have both. You cannot have the Marshallian atomless assumption and at the same time a strictly decreasing demand function. And actually, this was very surprising. This had been already observed by Stigler, who was a completely mainstream economist in the 50s in the Journal of Political Economy. So this is what you see here. So now, of course, you may say, well, we do have a theoretical problem here. It might be the case that we cannot have this kind of standard diagram, that we all teach in microeconomics 1.01, and at the same time perfect competition. But then if perfect competition doesn't hold, all this falls down, of course, okay? So you could think, well, we should replace the finite number of firms by a continuum, okay? But it happens that this does not help. And so the conclusion is that perfect competition makes no sense. There is another way to look at the same problem, which is essentially what I did in my PhD, which is that you could say, well, with a finite number of agents, households, and firms, you should essentially have imperfect competition. So you should have games à la Cournot or à la Bertrand, etc. But then when the number of players explodes to infinity, we should reach perfect competition. So perfect competition would be the analog to imperfect competition, as perfect gas are with respect to imperfect gas, okay? So, but it happens that this is not the case. There are strong negative results in this area. It's not true that imperfect competition, when the number of agents grows to infinity, leads to perfect competition. The situation is even worse, and this has been shown by Keen and Standish again. It's the fact that the profit maximization problem of firms is even wrong, intrinsically wrong. So the usual first order condition is here, as you remember. It's just that the firm is supposed to maximize its profit given the technological constraints imposed by its production set. And then the marginal condition is this one, that is the partial derivative of profit divided by the production program of firm J should be equal to 0. For instance, in the Goodwin-Keen model, this leads to this, as is well known. And so the main argument of Keen and Standish is to say, well, no, we should take the total derivative to make sure we don't miss anything, okay? So actually, we should take the total derivative of profit with respect to everything the profit depends upon, and then choose the right yj, okay? So if you do this, it happens that you end up with a completely different formula. So the first order formula is this one. I don't have time to go into the details because time is running, but you will be able to check this. And then you get this formula. So this aspect of the formula is the standard one, that is, the price should be equal to the marginal cost of production, okay? But now you have this additional factor here. And again, considering a continuum of firms does not help because then capital M will grow to infinity. And it happens that this formula is exactly the first order condition of an oligopole. In other words, if you take seriously the profit maximization program of a firm, you never get the perfect competitive first order condition. You always get the oligopolistic first order condition. Put it bluntly, perfect competition does not exist, simply. Now, I will finish very quickly with very important additional results. Some of them you already know, some of them you don't, I guess. Which come also from the 70s, the mid-70s, which is the identification problem, or in other words, everything is possible, anything is possible. If you look now at the aggregate excess demand here, which is the sum of the excess demand for each household, okay, for some price, P, then it's easy to see that the aggregate excess demand is a vector field on the unit sphere of prices. So first of all, you can normalize prices into the unit sphere. Why? Because as you have observed, the budget constraints are homogeneous of degree 1. So you can multiply or divide any price, the price vector by any positive coefficient. It doesn't change anything. So you can as well normalize prices into the unit sphere. So once you have done it, it's easy to see that as soon as you have strictly increasing preferences, the budget constraint will be always fulfilled as an equality, and therefore you have this. And therefore, the excess demand, the aggregate excess demand function, is a vector field here, as you see, on the surface of the positive as part of the unit sphere. Here you have an example of 3 commodities, okay? And an equilibrium, a variation equilibrium, is just a 0, like here, it's just a 0 of the aggregate excess demand. It's the place where we have found a price vector such that demand equals supply, okay? Now, and by the way, it's possible to prove existence using the very famous Poincaré-Hopf theorem on the sphere. Anyway, so here, now the main result, which goes back to Sonnenschein-Mantel-Debreu in the mid-70s, is that every continuous inward pointing vector field on the unit sphere, on the positive part of the unit sphere, can be decentralized or can be represented as the aggregate excess demand function of a well-chosen economy, okay? Economy here, provided you have enough households. In other words, as soon as the vector field here is inward pointing, that is, it points to the interior of the positive part of the unit sphere, then, and it is continuous, then it can be the aggregate excess demand of an economy. Completely non-pathological economy with completely rational people, etc., blah, blah, blah. And of course, this vector field can be completely pathological. So you may have chaos, you may have strange attractors, you may have a variety of attractors, etc., etc. So, so this was very bad news because first it proves that even in the complete market case, we may get trouble in studying equilibria, despite Debreu's nice theorem from 1970, showing that generically you have a finite number of equilibria which behave smoothly. And second, and this is even worse, it means that you cannot falsify general equilibrium theory, because general equilibrium theory, even with complete markets, tells you that there is no constraint on the aggregate excess demand, which is mainly the unique thing you can observe, except that it satisfies Valra's law, which is this. It is continuous and inward pointing on the boundary here, you see, of the unit sphere, which means that if the price of a commodity is equal to 0, then everybody wants to buy this commodity, which is not a surprise, okay? So apart from that, there is no restriction. So whatever you will be able to observe will be compatible with the theory. So you cannot build any experiment in order to try to falsify or to confirm the theory. So in the Popperian sense, this is not a scientific theory, you see? So there has been a lot of debates on that. Alan Kierman has written on this, Yves Balasco, etc., etc. Then some people hoped that by looking at incomplete markets, even though many economists don't like incomplete markets, we may have more structure that would prevent this anything goes result from happening. And unfortunately, it has been proven by Jean-Marc Bottazzi, another good friend, in 1994, that you have the same Sonnenschein-Mantel-Debreu theorem within complete markets. It's even worse than that. It has been proven by Ivar Ekland, another very good French economist, that the Sonnenschein-Mantel-Debreu theorem essentially holds even if you impose the income distribution. So even if you say, well, I want an economy which has this level of inequality, for instance, then whatever being the vector field that you observe on the unit sphere of prices, you may construct an economy which leads to this aggregate excess demand and has exactly the level of inequality you have imposed at the beginning. In other words, we have this situation, the market demand curve does not slope downward. It can have any shape, okay? So which means that we have this kind of situation here. So on the top, that's the usual diagram that we teach in micro, 1.01, and at the bottom here, it's reality. That is, you have an emergent phenomenon and everything is essentially possible, which is bad news. Now, you have exactly the same result on the supply side. I don't have time to explain this. This has been, it's a beautiful result proven by Andreu Mascolen, a very nice guy who was working at Harvard, and then he became the Minister of Higher Education in Catalonia, in Spain, a very good friend. So Andreu proved that you have the same result for the supply side. So which means essentially that this diagram is definitely wrong, okay? And then the last point, and I will stop here in 2 minutes, on preferences. So as we have seen, the main idea that variation equilibria leads to Pareto optimal allocations is very fragile, to say the least. Even the existence of equilibria is very fragile. Even the existence of a downward sloping demand, aggregate demand function is very fragile. And the existence of an upward sloping supply function is very fragile, to say the least. Now, what about utility functions and preferences? So in order to represent preferences by a utility function, you need to make sure that your preferences are complete, meaning that you can compare any type of consumption baskets. So if I ask you, do you prefer to listen to, Monteverdi versus to listen to Scriabin, you must have an idea. You must prefer one to the other. We don't care about whether you prefer Monteverdi to Scriabin, but you must know both composers and you must have an idea about whether you prefer one to the other. And this is true for everything. So that's the completeness assumption. And of course, needless to say, I mean, we don't have complete preferences in the world. Second axiom, you need transitivity. That is, if you prefer A to B and you prefer B to C, you must prefer A to C. And there are a number of experimental economics, experiments in economics, which show that human beings don't have transitive preferences. You prefer, I don't know, you prefer Roger Federer to Ivan Lendl, and you prefer Ivan Lendl to, I don't know, Bjorn Borg, but you prefer Bjorn Borg to Roger Federer. Why not? So, and you need some form of continuity. Otherwise, you cannot represent the utility function. So, in other words, you need to have these kind of preferences, where this is this set here is this curve is an indifference curve of your agent. So it's very it's very difficult to claim that it makes sense to represent a preference with a utility function, given the strength of the axioms that need to be fulfilled by these preferences in order for this utility function to exist. Now, we said that the utility function UI represents a preference, a pre-order, if and only if when X is preferred to Y weakly, then UI of X is larger than UI of Y here. Now, immediately you observe that if you take any strictly increasing function f from R to R, then the composition of f with UI also represents the same preferences. In other words, you don't have the uniqueness of the utility function, no way. Actually, you have an infinite dimensional space of functions which can represent the same preferences. So when you deal only with preferences, we say that the theory is ordinal. When you deal with a specific choice of a utility or a subclass of utilities, we say that your theory is cardinal. Now, if you use cardinal utilities, then you can, for instance, describe a social welfare function. You can, for instance, if you are a utilitarian, you can decide that, you know, as a social planner, you want to maximize the sum of the utilities of people. And you see that this is a completely cardinal concept because you are summing the functions, which means that, for instance, if we suppose that here it is a function of Paul, and there is a function of Loic, and suppose I multiply the function of Loic by 1 million, and I divide the function of Paul by 1 million, then most probably I'm going to maximize in a way which is very in favor of Loic and not in favor of Paul. But both utility functions represent both Loic's and Paul's preferences. So you see that the utilitarian criterion is completely dependent upon the cardinal choice of a utility function. Same story for the Rawlsian-Maximin criterion here. And on top of that, not only are these cardinal concepts, but they also use interpersonal comparison of utilities. That is, by doing this, I'm comparing 1 unit of utility of Paul with 1 unit of utility of Loic. Okay, so from a normative viewpoint, from an ethical viewpoint, I think everybody agrees that the cardinal welfare theory is not acceptable. Then the question is, can we do something with an ordinal welfare theory? Okay, that's the main big question. And this is where all the theory about the weak axiom of revealed preferences enters the picture. What is this? It's simply the idea that, well, the utility function is not observable. I mean, it does not exist. It's an artifact of our theory. And preferences do exist, but can we observe them in a reliable way? That's the main question. The answer is yes, if they satisfy the weak axiom of revealed preferences. This axiom says the following. Suppose that you are one agent here and you have a first budget set, which is this one, okay? So the first price you observe is P1. And it happens that at this price, you prefer A to B because you buy A and you don't purchase B, okay? So we say then that you revealed that your preferences put more weight to A than to B. So A is preferred to B, okay? Now, suppose that now you observe P2, okay? And with P2, you prefer B to C, okay? Then here you have B, which is preferred to C. Then you will say, well, with this new budget, we know that B is preferred to C, and by transitivity, you have this, okay? Now, suppose that you have the following situation here. So you have both A and B, which belongs to the budget set with P1. A is preferred to D, another one, D, with D. So A belongs to the argmax, let's say, of your household in the budget set given by P1, and B belongs now to the budget set with P2, and B belongs to the argmax, okay? And I should add something like, yeah, of course, A is different. Sorry, A is preferred to B. Then it cannot be the case that A belongs to the budget set with P2, because then A should be preferred to B, and B cannot be in the argmax of the household, okay? So this is the revealed, so to say, a kind of revealed transitivity. And so provided your preferences satisfy this weak axiom of revealed preferences, then we should be able, at least theoretically, to observe your preferences and to deduce your preferences from your behavior, from your purchasing behavior in a store every day. Now, the main problem with this classical theory is that, first, as I said, experimental economics tells you that our preferences are not transitive, they're not complete, they're often very discontinuous. And second, there is also a much deeper problem, which is that outside the lab of experimental economics, so in real life, we cannot observe the budget set in the very first place. In other words, what we observe empirically it's this. So it happens that with this price P1, you purchase A, but we don't know whether you were aware of the fact that you could have purchased this, you could have purchased this point or this point. We don't know exactly what you know. Maybe you only, investigated locally here. And so for this subset, A is your preferred bundle. We don't know actually. We cannot ask you what is the set of commodity bundles or commodity baskets that you have investigated before choosing A. We just don't know. So in other words, outside of the lab, this is completely useless. So in the lab, it's easy because in the lab, we describe everything to the subject. That is, we tell him or her, look, the price is P1 and your budget set is given by this, so you can purchase everything in this triangle, blah, 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 and what is your choice? And then the subject reveals his or her preferences. Now, in real life, you cannot. So this was the main argument of Amartya Sen, a big guy from India, as you know, who got the Nobel Award, saying essentially, well, utility theory is useless because you cannot observe the budget set of an agent. And I will stop here. Thank you for listening.
Thank you very much, Gaël, for this presentation. I think we can, as usual, open the floor for questions, and as pretty much everybody's online, it's up to you to raise your hand. Yeah, Alejandro?
Yeah. Yep. Yes, do you hear me?
Yeah.
Yep, okay. Gaël, congratulations.
Thank you
for this presentation, because you have given a review from Valras 2 centuries ago, more or less to the current situation, the macroeconomic theory right now in general equilibrium. I'm not so sure, but probably reading the Masculine, Wister and Green book, Macroeconomic Theory, you have not talked, I think you have not talked about dynamic games, game theory, externalities and public goods, but the rest is included in your presentation. So it's very difficult to ask something concrete, but perhaps moving is your knowledge about the theory. The main message of the general equilibrium theory right now can be that you think can be moved to the applied general equilibrium to do something more realistic. What could be your big or main message after this big and very, very intensive revision?
Well, you know,
if there is something, I don't know.
So the answer, to be very honest with you, and this is among us, I don't know whether we are recorded, is the true answer is I don't know, because I think you honestly know this better than I do, in the sense that I have very little experience of, CGE with input-output matrices and the way they work when they are applied to economics. All what I can say is that from a theoretical viewpoint, definitely general equilibrium theory does not provide the standard classical picture that people have in mind when they think of general equilibrium theory, because essentially the main message is exactly the opposite. That is, free market, believers should know better general equilibrium theory to understand that general equilibrium theory proves that financial markets are incomplete, inefficient, subject to sunspot, equilibria do not exist, blah, 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 all this. Usually this is not taught. What happens sometimes when you have lectures on incomplete markets, people teach incomplete markets with one commodity. And it happens that with one commodity, all the negative results I was alluding to disappear. You still have positive results. So, and very often, at least this was my experience, the prof would say, well, with multiple commodities, it's much more complicated. There's a lot of math. So we will do this next year. And it's never done. So that's the main point. So there is, on the theoretical side, there is a big challenge today, I believe. And to give you an anecdote, General Debreu, whom I knew quite well in the 90s, starting in the late 70s, when he discovered his own theorem, the Sonnenschein-Mantel-Debreu theorem, stopped completely working on general equilibrium theory because of the non-falsifiability of the theory. This does not mean that using a CGE with IO is not useful, but it means that from a purely epistemological viewpoint, the theory as a theory does not provide any constraint about things that you can observe. You see, and so so I went to a number of seminars with Gerard, and he would sit at the first row, you know, and would never say anything, would never ask any question, would be completely mute. So everybody was impressed, you know. Oh, he's thinking probably, you know, but actually he had decided to withdraw completely from the whole academic debate.
Yeah. Talking about General Debreu, remember that I told you that he was the PhD advisor of my advisor in Berkeley, and the title of the PhD of my PhD advisor was exactly The Core of General Equilibrium, and was done at the end of the 80s in the last century.
Yeah.
Okay, but it is true that sometimes we are in parallel world, applied and theory. Sometimes we converge, very strategic word talking about general equilibrium, but sometimes we are not in the same line. But
sure.
Okay, it's the problem, the bridge between the economic theory and applied economics. It's only to try to do this.
In applied situations, you do everything so that you have an equilibrium, etc., etc. So you avoid by construction all the pathologies that I was describing. Now it's interesting to, I mean, and probably for completely applied viewpoint, it's not that, you know, it's fine. But from a purely theoretical viewpoint, it's very important to be able to say, to tell to everybody, you know, usually equilibria do not exist, perfect competition does not make sense, etc., etc. You know, so that's very important, I believe.
Okay, thank you again, and congratulations.
Thank you.
Very funny, the presentation using this blackboard has been very funny.
Yeah, Camille.
Yeah, thank you, Gaël, for this really wide presentation. 2 questions. In the framework of our activities about ecological transition, economic planning, what would be for us a consistent new research program in terms of general equilibrium? And the other question would be, would you have some insights about the potential use of non-smooth analysis?
So the second question is easy. Non-smooth analysis has already been used, especially in production theory, because there is no reason to assume that the production set is smooth. So you remember, maybe I can share again if you want. So you see my screen? Yeah. So here, if I go back to this, oops, let me refresh, wait a minute. Yeah. If I go back to this here, so you remember that I said that essentially what's happening is that here we consider the boundary of the production set, which is this, this thing here, okay? And then we look at the gradient of the production function, whose graph is exactly this boundary. So this is the standard way to do it. Of course, there is no reason to assume that the production set is smooth. You may perfectly have a production set which is like this, you know, with a lot of non-differentiabilities. And this is where you need non-smooth analysis. Same story for utilities. There is no reason to assume that utility functions are smooth, and so you can use non-smooth analysis. So this has been used in general equilibrium theory, especially by the team with Cornet, Bonisso, all these guys. Yeah, so this is already done, more or less well known. This is an area which has been already explored, but the economic substance of this is, I believe, rather weak. That is, it's funny for mathematicians, but it does not provide a lot of insight from an economic viewpoint. Now, to answer to your first question, which is more tricky, my position, but that's only me, is that we should essentially develop and extend both Goodwin on the one hand and Solow on the other hand. That is, these out of equilibrium macroeconomic dynamics. You know, where there is no reason to assume that you have a single commodity, as Solo assumed. This is definitely not true. So we definitely have to enter into the multi-commodity world. There is no reason to assume that there is a production function. We know that it doesn't exist. So we should replace the production function by a production set, and then we would have a dynamics. If I can draw a picture here. So you have a production set, let's say, like this, which need not be convex, because in real life things are not convex. And then you would have, you know, a vector space which would move here along the boundary, whose dynamics would be given by something like a Goodwin-King model or Solo model, etc., etc. You see, I believe that's the very interesting area of research. And then, of course, again, the boundary has no reason to be smooth, so there is no reason to assume that you have a well-behaved differential equations like this. So F is not smooth in real life, but it's not even continuous. So you need tools from non-smooth analysis. So the big guy who has written on this is Clark. I think I already gave you the reference of Clark, you know. And also in France, there is Jean-Pierre Robin, and in Italy, Arrigo Cellina. So they have provided the main tools that we need in order to deal with this when F is not smooth. And of course, there is also the Filipov theorem. Makes sense. Okay. Any other question? Clémence, you are muted.
Yeah, sorry, I was just asking if somebody had another question.
No question. We don't have free market believers here.
All right. I mean, anyway, we were almost running out of time, so we might just end here.
You're welcome. So I
Absolutely
will,
no
I will keep
questions.
the my notes, even though my handwriting is very bad. But I hope you can read it if you're interested in. I think Weye, for instance, for you, it's very good to learn this. And I'm sure you have never been taught what I said today. Well, none of you, I mean, apart from Alejandro, who did already hear this, the whole story in the
I think
classroom.
I did that.
Hmm? Did you, Clemens?
Yep.
Within complete markets and all this? I'm surprised.
Mm-hmm.
Where do they teach that?
No, I also had heterodox teachers.
Say it again?
I said I also had heterodox teachers.
Ah, but that's not heterodox. That's completely orthodox.
No, sure, but they were more prone to present it.
I can hear you.
I said they were more prone to present it than pure orthodox teachers, I would say.
Yeah, but you know, it's just the orthodox theory. I mean, John Giannakopoulos,
Sure.
Polymarchakis are really great guys
Absolutely.
in general economic theory. It's not a question of being orthodox or heterodox. Just it's a question of knowing his own theory.
Yep,
the problem is
that's
that
right.
many economists don't even know general economic theory. They just know the first chapter, and that's it.
All right. So if there really isn't any question left, I think we can just end here. And thank you again, everybody, for attending. Thank you, Gaël, for this very useful and informative presentation. Very interesting too. And I think our next session will be on March the 2nd, but of course you will receive the emails as usual. So thanks and
Thank you.
have a good day.
Thank you. Gracias.
Bye.
Bye, Gaël. Thank
Bye.
you. Bye-bye.
Hasta luego.